Welcome to Lesson 29. So we're going to talk about the matched pairs T procedures. In Lesson 28, we talked about when we had two independent populations. Now we're going to talk about having two dependent populations. So first we're going to define what that is, and then we're going to go into how to do a confidence interval and hypothesis test for this situation. So independence and dependence. In general, you can think of populations as independent if you know that they are totally unrelated. So the observations from population 1 cannot also be observed in population 2. They only belong to one population at a time. They do need to be unrelated. However, we consider them dependent or paired when we have an observation that is in both populations. Especially in the case of when you have every observation is in both. The most common are like repeated measurements. So you might have before and after measurements. Like before and after like a weight loss program, or before and after a SAT study prep program. I don't know. Those are the ones you'll find online a lot. Testing on twins or genetically identical or very similar individuals. You'll definitely see sibling studies a lot. Twin studies, yes. Splitting a sample to impose more than one treatment on a single unit. So you might see this like when people have one plot of land and they split it in two and they give treatment 1 and for half and treatment 2 in the other. Hopefully they split it in more than 2. But one example would be real smart of bioscience lab had this lab right across the way from Montana State, and they would go ahead and they would recruit folks, give them, I don't know, a few $100s or whatever to participate in studies. It was a good way to make, some extra grocery money. So one of them, they were testing some sort of new ink, and they went ahead, they had a new ink and an old ink, and they tested one of the inks on my right arm, and then they tested the other ink on the other arm. And the idea is that this would be matched pairs because how my skin reacts on one arm is related to how my skin reacts on another arm. So they want to keep those together. They want to specifically look at the differences between my right arm and my left arm. So that would be an example. Repeated measurements before and after, pre and post, those are really, really common examples. Any scenario where you have sample 1 and sample 2 and you notice they have the same exact, like you could line up the observations. That's the idea. So we are going to have just an example here where we give you 2 studies, and you have to determine which one has 2 independent populations and which one has 2 dependent populations. Absolutely, this is an excellent place to pause, read them over, and then go ahead and try and answer for yourself. So I'll give you a second, but then I'll go through each one. Okay, so in study 1, because apparently we're very fixated on attitudes towards statistics and feel that we can capture this in a survey, because okay, sure. So we want to look at a particular professor. They want to look at the change in attitude towards stats over the course of a semester. So the professor goes ahead, they take a simple random sample of the students in their classes. They give a questionnaire to the students at the beginning of the semester, and then they go ahead, they track down the same students and they give them the same questionnaire at the end of the semester. So here, one thing to consider is you have something at the beginning of the term and something at the end. And not only that is you have the same participants at both ends. So person 1 took it at the beginning and at the end. This is a pre and post scenario. These will be dependent populations, because each person is in each sample. That's what it comes down to. So they're in both samples. So each person's in both samples. Study 2, at the end of a term, a stats professor still really, really wants to know about attitudes towards stats, and they think a survey can measure it. So they go ahead and they take a sample of science-based majors and they take a sample of non-science-based majors. Because, nobody double majors, right? So they go ahead, they take a simple random sample of each, and they administer the questionnaire. So here, as long as you can fairly assume that the group of science-based majors and the group of non-science-based majors have no one in common and no one's in both of these groups, you can say these will be independent. Once again, humans tend to be a little unpredictable. There are going to be some people that double major. I definitely have met more than one person that's majored in stats and psychology, and I think several groups would say that's a science-based and a non-science-based major. Totally depends on the perspective there. However, as long as you exclude those people from the populations when you sample, you would have independent populations here. But you would have to specify that those are the populations you're comparing. Specifically people that have not double majored in both. Okay, so here's an example. We're going to go with the attitude towards statistics survey. We have 13 randomly sampled students, and they were given the survey. Probably this is there's a question, and it's Likert scale, like 1 being strongly dislike, 10 being strongly agree or strongly like, I don't know. But we have 13 students. They're labeled by letter, which I think is a little unfortunate. I would rather call them like student 1, student 2. So here we have student A. This is student A's before score on this questionnaire. This is student A's after score on the survey. And that's one thing that's super important is when you have something matched like this, they need to line up exactly. Student B's before needs to line up with student B's after. It can't line up with student, J's after. That won't work. So from there, what we're going to do, what we could do, you could treat it as if it were 2 independent groups. So ignore the matching that's actually there and compare the mean from the before group and the mean from the after. And you can see here that the spread's definitely different, definitely wider in the before. But if you do this, you do a 2-sample t-test, you're going to find there's not a significant difference. You're going to get a fairly large p-value of 0.12. However, if you use matched pairs methods, which is the one that's appropriate to use in this instance, so now we're looking at differences. So after minus before. So if you look at difference 1, it's student A's after minus student A's before to get 4. You'll find that a lot of times we'll subtract in whatever order is going to give us fewer negative numbers. It's a personal preference. It's not required. You could have absolutely done before minus after. So I did that there. And you look at difference in attitude towards statistics. So now one thing to think about is, on average, if people didn't change at all, this difference would be near 0. So do we think that the average difference in attitude is 0? If you run the paired t-test, you're going to find that there is significant evidence that there is a difference in attitude. So absolutely, if you perform that independent 2-sample t-test, you are going to increase your type 2 error versus if you correctly perform a paired t-test. In general, you're just going to have a lot more information if you run a paired t-test. So this is the example we're going to use throughout this particular lesson. We have 4 random samples, which is not a lot, I admit, of a ferrous type, so think iron, right? Substance used to determine if there's a difference between the lab chem analysis and X-ray fluorescence analysis. So they have two ways to analyze it and determine how much iron content is in it. And if you have 4 samples and split them in half, sample 1, if you split it in 2, it should have the same amount of, or same iron content in both. Ideally, the 2 methods would probably show the same amount, but if they don't, that indicates that one is detecting more iron than the other. So each sample is split. So we take the 4 samples and we split them. So technically we have like 2 subsamples for each of these samples. So 8 subsamples total. And we analyze using both methods. We did something similar once in a chem class that we had, that we all had the same thing that we weighed, but we all used different scales, and we found that there was some variability in the scales. So when data are paired, we can make comparisons by specifically just looking at the differences. So here we have chem and we have X-ray. If you do chem minus X-ray, right here, your first difference is 0.1, your second difference is 0.2, third difference is 0.2. We can analyze just the differences. That's what a paired t-test does, is it analyzes just the differences. So here, some notation that we're going to introduce. D bar, if you think of this as D1, D2, D3, D4, because we have 4 differences. And honestly, it doesn't matter which order you do them in. I'm just labeling them here. Is if you add all these differences together and divide by the number of differences, so ND is the number of differences here. There's 4 of them. So if I add 0.1 plus 0.2 plus 0.2 plus 0.1, divide by 4, I'm going to get the average difference in my samples. And then same as if I go ahead and I can find the standard deviation of these differences, and that's going to be S sub D. So that D subscript is indicating that this is the standard deviation of the differences. So the bar means average. This is the average of the differences. This is the sample size of the differences. That's the idea. And it is really important that you are very consistent in the order you subtract in. If you do chem minus X-ray, you can't mix it up when you feel like it. It has to be chem minus X-ray for all of them. You're absolutely, totally allowed to do X-ray minus chemical, but you have to do it for all 4 differences. You have to be consistent. So if I'm doing a confidence interval here, this is essentially what we end up doing is it's going to be like taking a 1 sample T methods or T procedures on the differences. So if you only look at the differences, usually column in a data set, and doing 1 sample T procedures on that difference column. So here we want to find we want to estimate the mean difference or the average difference. So this is where it's appropriate to say mean difference. That's okay. Between 2 dependent populations. So here we still want the samples to be representative of the population. So wherever the sample came from, hopefully they took the sample well. Hopefully it was a random sample. We do want the number of differences to be big enough such that the sampling distribution of D bar is going to be approximately normal. So like for our iron example, a sample of 4 is pretty small. Hopefully they're going to tell us that population of differences is going to be normal. And then here, this is where usually it's often this third condition, populations are dependent or the data are paired. So you want them paired, and we're going to focus on, so you might have the first, the pre and the post, and then you're going to have a differences column. You're only going to analyze the differences. So if I want to do confidence interval, I'm going to find the average difference from my samples times T star. So my T star critical value, because we're using T procedures, I have to use a T star critical value. times the standard error for the differences, which the standard error for the differences is just the standard deviation of the differences over the square root of the number of differences in the sample. So our degrees of freedom, it's really nice because one giveaway if you're doing a matched pairs test is that the sample size between the two groups has to be the same. It must always be the same. Like, it was convenient that the two in lesson, the last lesson, lesson 28, had the same sample size, but by no means for a two sample t-test is it required that they have the same sample sizes. For paired, it is required. They have to have the same. And then, yeah, there's our standard error there. And yeah, okay. So here we're going to still focus on this iron detection example. So we have 4 samples of, let me see, ferrous type substance. They go ahead, they split each of these 4 samples up, and they test it with the X-ray fluorescence and the chemical analysis. And we want to look at the difference here. So let's estimate. So estimate is like an indicator, like it should be like ding, like I'm going to do a confidence interval. We want to look at the average difference. So average difference or mean difference between iron content of the different measuring methods. So here, what is my question of interest? If you're doing a confidence interval right off the bat, that tells me that this question, it should be open-ended. So here, going to be, what is the mean difference? So what is the mean difference in iron content detected? Oops. Nope, too close. Between chemical analysis and X-ray analysis. You could absolutely say X-ray fluorescence analysis. Probably be more accurate. And because I'm doing subtraction here, I do need to specify so that I did chem minus X-ray. Because if I estimate that this difference is positive versus negative, that indicates that the iron content detected is higher in one of the methods there. So it is important to keep track of that subtraction direction. So my parameter of interest, it's now the mean difference. Because I'm only looking at the difference column, I want to know about the mean of all the differences. So it's the mean difference. Oops. In iron content detected. Steps 1 and 2 should sound very repetitive. If you have step 1 set up correctly, you have half of step 2. So in iron content detected, between chemical analysis and X-ray fluorescence, analysis. And then I am going to write again. It's chem minus X-ray. So my inventory, so remember I'm focusing on the differences here. So my mean difference, so if I take the 0.1 plus 0.2 plus 0.2 plus 0.1, divide by 4, I end up getting 0.1 0.15. I don't know the units. So I'm just going to acknowledge that I don't know the units. And if there is a circumstance like that where we don't tell you what the units are and they're not obvious, you can absolutely feel free to reach out and clarify with us, hey, are there units here? But in general, if we don't include the units, we don't necessarily expect you to do this research, go out and Google and find exactly what they should be. So keep that in mind. Like, there probably are units, but we don't know what they are here. Goodness knows, I had at least one paper that I ended up writing out my analysis with snow units because they didn't tell us what the units were. So that was fun. So the number of differences, that one's a little straightforward, is 4. And then the standard deviation of those differences is about 0.058. And I'm going to write units again, but I'm not going to focus too much on them in the future there. So this would be my inventory. I know the average difference observed in the samples. I know that there are 4 differences, and I know that the standard deviation of those differences. So things to consider before we go there. Did they tell us? You will see. So 4 random samples of this fair. So do we have our data from a random representative sample? They tell us that it's 4 random samples. So yes, that's okay. We do have random samples. And this is the hazard of copy and paste, you might see. Do we have a large enough sample of differences here? Depends. ND is equal to 4. It's very small. So we will need information like it's going to be really, really difficult, quite honestly, to say whether or not these are normally distributed with a sample of only 4. Definitely far from ideal. This is probably definitely worth like an asterisk at the end, like may not, like have the central limit theorem kick in. It's definitely really hard to tell with only samples of 4. It's really, really difficult. So here, you notice I crossed out, are the populations dependent? They are matched. So they are matched. Each sample is analyzed with both methods. So sample 1 is measured, the iron content's measured with X-ray fluorescence analysis and the chemical analysis. So yes, it is matched. This one is a little worrisome. That one, you should definitely write, hey, we don't know if this one's met. Unless they tell us that we can assume that those differences are normal, this is really, really sketchy. It does not mean we're going to stop and not run the analysis, but you should absolutely write somewhere a disclaimer. Hey, we don't know that this is true. This is problematic. Absolutely. Step 3, my confidence level. So we wanted to do, I believe, was it a 90% confidence interval here? So, and it's a 90% confidence interval for mu d, because this is the parameter we're interested in estimating. So our degrees of freedom, they're not going to be very big because our sample's not very big, which means we're going to end up with a really wide t-distribution. And that's what happens when you take small samples. So 4 minus 1 is equal to 3. So now I have the information. I know which column I need. I know which row I need. So I need degree of freedom 3 row. And I need the 90% column. So my T star critical value. T star critical value for 90% confidence interval when my degrees of freedom are 3 is going to be 2.353, which is pretty big actually. But that's what happens when you have a really small sample size. And that's kind of one of the things that the t-distribution does. Is if you have a small sample size, it kind of means that it uses a wider reference distribution. You need like much more extreme differences to actually be detected in hypothesis tests, all that kind of fun stuff. Okay, so setting this up, 0.15, 2.353, 0.053. I'm not writing the units right now because I don't know them. My degrees of freedom are 3. So I have everything I need to plug in here. So the average difference I saw in my samples, it was really, really small sample. And then my t-star is 2.353 times 0.053 over the square root of 4. That's nice. That's actually math. That's very doable for me. So I end up getting, so this is my point estimate. This is my critical value. This right here is my standard error. Everything after the plus or minus is my margin of error. So this is my margin of error. This is my t-star critical value. Standard error. I'm just throwing that out. Oh, this is my point estimate. Because we love to give something like this and ask what the value of the margin of error versus the standard error. We like to have you differentiate that for us. So 0.15 plus or minus 0.068, probably did some rounding there, is equal to, put the smaller one first, 0.082, I'm going to write units, to 0.218 units. So there's my confidence interval. So when we want to calculate the confidence interval, we're a big fan of putting it in interval notation. The lower value should be on the left, the higher value should be on the right. If you know units, you should include them. And know that the units thing will only apply to quantitative variables. When we get to categorical variables, we won't have units. We'll be doing proportions. So writing this up, so this is a 90. Once again, hazards of copy and paste, right? So 0.082 to 0.218, the 90% confidence interval. So now my parameter of interest, mean difference, in what? So in iron content measured. I'm going to write between the chemical analysis and X-ray analysis. I might not have left enough space to write on here. And I'm going to write X-ray analysis, not the X-ray fluorescence analysis. I didn't leave space. Is on average estimated to be between 0.082 units if you had them, and 0.218. So here we did chem minus X-ray. And we get positive endpoints, so positive 0.082 and positive 0.218. This indicates that on average we estimate that the chemical analysis finds more, detects a higher iron content than the X-ray analysis does. So I'm going to put that in here. So higher for chemical analysis. This is me inserting the direction I subtracted in, or the information there, with a point estimate of, so what I saw in the samples, 0.15 higher for chemical analysis. And there you go. But once again, the sample was a 4. We definitely have issues saying we believe that the differences of the population, so if all the all of the analyses done for all samples you could take with X-ray analysis and chemical analysis and take the differences. That population of differences, we don't know if it's normal. We hope it is, but from our differences, we had 0.1, 0.1, 0.2, 0.2. That's not going to look necessarily normal. It's not going to look not normal. It's going to look like a rectangle. F4 is small. If you can avoid having that small of a sample, that'd be great. But there are instances where you just really can't. So it gets complicated. Now that we've done the confidence interval, we're going to go ahead and do the hypothesis test version. So before we wanted to estimate, now we want to test the average difference, mu d, between two dependent populations. So we want to know that the samples are representative of the population, so we took a random sample, or random samples, well, depends. And we can count on the central limit theorem kicking in because the number of differences we have is big enough, and or like if you were to put the differences into a histogram, it would look roughly normal. So either they have to look roughly normal, or you have to have usually at least 30 or so. We really didn't meet either of those with that ferrous substance example. That one is definitely iffy. Just a caution there. And then populations are dependent, or the data are paired. So here we're going to say, okay, well that mean difference is equal to some claimed difference amount. Almost always, this is going to be 0. Every once in a while it's something else, but most of the time it's 0. You could say, oh, this such and such weight loss program advertised that people lose 15 pounds in their program on average. Then you would have a different value. But most of the time that we run these tests, we're interested in a difference of 0. So when we, you can have the lower one-sided, upper one-sided. This is where it's really important to keep track of which way you're subtracting. So like I was doing chem minus x-ray. If I had been doing it the other way around, it would have flipped. Like they would have been in one could have been a lower and one could have been an upper depending on which way I was subtracting. But you can also absolutely do a two-sided. And when you do that, because obviously we don't know any standard deviation of populations, our test statistic is going to be a t-test statistic. So we're going to take the average difference we saw from the samples minus the claim difference, which almost always is 0, over the standard deviation of the differences over square root of the differences. In our reference distribution, it's going to be a t-distribution with degrees of freedom that are equal to the number of differences minus 1. So welcome back to our example, because we really, really love to stick with one example all the way through. So now we want to test whether there's evidence the two methods measure a different amount. So whether there is, that tells me, hey, whether there or not there is this, it's like a yes or no type structure there, a different amount. So this tells me that I don't necessarily suspect one or the other is higher or lower. I just want to know if they're different. Because remember, you don't look at the sample before you write your question of interest and your hypotheses. We are going to use a significance level of 0.10. Here we go. Assume the population of differences is normally distributed. That's what we needed. I'm not sure why it wasn't written earlier, but we needed it. So what is my question of interest? If I'm doing a hypothesis test, a matched pairs t-test here, this is going to be written as a yes or no question. So most of the time I'm going to start it with is. So is the mean difference. So is the mean difference in iron content detected? between the two, between chemical analysis and X-ray analysis. And I am going to put the order I subtracted in, so chem minus X-ray. Is that different than 0? So is the mean difference in iron content detected between chem analysis and X-ray analysis, specifically chem minus X-ray, is that different than 0? And trust me, sometimes getting the wording right in these, it gets a little awkward. I absolutely, matched pairs t-test conclusions can be written very awkwardly. It's real funky sometimes. So here, my parameter of interest is going to be the same as when I was doing that confidence interval. So I'm still looking at the mean difference. So mean difference, but then I need information about like mean difference in what. So in iron content detected between those two methods. So between chem analysis, chemical analysis. I know, I'm sorry, this is so not exciting because I'm writing. Maybe I might try filling this in with automatic next time. An X-ray analysis. And I want chem minus X-ray. So there we go. Step 2, in general, most of the time, pretty much, step 2 is going to look identical whether you're doing a hypothesis test or a confidence interval. So if you're doing a hypothesis test and a confidence interval for the same problem, step 2 should be the same between the two. Most of the time, the conditions will be the same, but not always. It's not this week, maybe next week. When we get into Z procedures for proportion, that's when it changes up a little bit. So my inventory is going to look a lot like last time. So the mean difference I saw in my samples was 0.15. Standard deviation I saw in my samples, 0.058. Once again, I don't know the units there. The number of differences was 4, which means my degrees of freedom will be 3. 4 minus 1. But because it is a hypothesis test, my null difference, that's going to be 0. Because the really uninteresting scenario is if the two methods have the same exact iron content detected. That means that the differences on average will be 0. So significance level, alpha equals 0.10. So here, for my hypotheses, my parameter is mu d, so the mean difference, it will always be an equal sign in the null. So null, default, 0. And then 0. If there were units, I would put them. I don't know what they are. You're also going to have the same null claimed value in the alternative. What changes here is the sign. It will not be an equal sign. And this is going to be based on, is there evidence the two methods measure a different amount? So different doesn't tell me, hey, I think one's higher or one's lower specifically. So I'm just going to say, hey, they're not equal. So this is boring, null, like they're the same. The alternative is saying, no, they're not. The differences on average aren't 0 because they're measuring differently. So yeah, different doesn't imply one particular direction or the other. It doesn't imply that I have this mindset that chemical analysis detects more or vice versa. And in general, so you won't look at this to actually make this decision. You will only look at the prompt. That's how you make the hypothesis test. Otherwise, it is cheating. It is watching the race and then placing your bets. That's super not allowed. In theory, you wouldn't even have this data set to look at to possibly, taint your idea of what should happen. So checking my conditions. We did take a random sample. Those 4 samples, ferrous substance samples, were randomly selected from where? I don't know. That might be worth investigating because I doubt they're from everywhere in the world. So based on central limit theorem, the number of differences is high enough. This is true because the population of differences is normal. So anytime that you know that the populations are normal, any sample size will be big enough. However, it gets a lot fishier if you don't know that they're normal. A lot of times you won't know. So in general, then you're going to want to have a bigger sample size. So if you have samples of at least 30, usually this will be good enough for this to kick in as well. And then data are dependent or data is paired. Are paired? Yes. Because data are plural, right? You've got data is plural and datum is singular. Just a weird thing, like bacterium, right? People don't think about it a lot. I had one teacher that would just light up your paper if you wrote data is anywhere. So calculate the test statistic and p-value. So now I've done all the steps. I've checked the conditions. I know I'm okay to go. So it's going to be 0.15 here, 0.058. My sample size, I had 4 differences. Degrees of freedom 3, that's 0. I love when this is 0. It's almost always 0 because anything minus 0 is just itself. So what I saw in the sample, 0.15 minus 0, easy peasy up top, divided by 0.58 divided by the square root of 4. So ends up being what? 0.3 divided by 0.58. All I did was use fraction rules and I put the square root of 4 up top. And that's going to be 5.17 is my T test statistic. Not only that, is if I want to find a p-value, I'm going to use a T distribution with 3 degrees of freedom as my reference distribution. So, to my t-table. My t-stat, it's going to be 5.17. So in general, if the null were true, the differences would be 0. We saw 0.15, so 0.15 or higher. This area is going to be our, this upper area is going to be our one-sided p-value. Remember, if we want two-sided, we also have to multiply that by 2. So, my degrees of freedom, they're 3. So I'm going to use this information here to find my one-sided p-value. So I need a 3 row, and then I need to look in here for where 5.17 lives, right? Usually it lives between a couple of these numbers. It could live off the edge. That happens as well. But yeah, looking here, no, it's out. It's definitely going to be inside. So I've got 5.8. That's bigger than it. Okay. So my test statistic, 5.17, it's somewhere between these two numbers, right? It's somewhere in there. So I'm going to go up and say, okay, well, my one-sided p-value is between those two numbers. So my one-sided p-value is between, the smaller one's 0.005, the bigger one's 0.01. However, this is a one-sided p-value. I am doing a two-sided test because that the alternative hypothesis has a not equal sign, that means I need a two-sided p-value. So in order to get there, I need to multiply everything in this inequality by 2. So I'm going to get 0.01 is less than my two-sided p-value is less than 0.02. So my two-sided p-value is going to be between 0.01 and 0.02. Not super specific, but specific enough that I will be able to know whether or not I should reject it. Because my significance level is 0.10. My p-value is definitely below 0.10. If it's between 1 and 2%, it's definitely less than 10%. So here, I'm going to say that was a two-sided t-test statistic for a, what was it? It was 5.17 at 0.10 with a p-value between 0.01 and 0.02. Note if I use R, usually I do have that right here. I got 0.014, that's more specific. That is between 0.01 and 0.02, so I'm happy. You should be very unhappy if you find a p-value that's not between the numbers you found. It usually indicates something went wrong somewhere. Usually it has to do with multiplying by 2 because you go from a one-sided p-value to a two-sided p-value. So once again we said, hey, this is a small p-value. It's smaller than 0.10, so we're going to reject. The idea is if the average difference in iron detected between the two methods really was 0, the probability that we would have seen differences that were 0.15 in either direction or bigger, that would only happen about 1.4% of the time if the null really were true. So that's enough evidence to make us say, you know what, I suspect the null isn't true. So here, I'd say there's probably strong evidence to suggest that, and now we're going to put the alternative in words, in context. So that the mean difference in iron content detected between the two methods and I'll probably put it in here, so chem analysis and X-ray analysis is not 0. And that's a weird thing, like a weird wording, at least in general, in English. So it's saying, basically, a translation here is, on average, the iron content detected, between the two methods differ. So it's saying, yeah, on average, it does look like the iron detected between the two methods, they differ. I would be more specific, I would mention what the two methods are, but that is the gist of it. It's a bit more awkward to say, oh, no, we have strong evidence. That mean is not equal to 0. Well, in layman's terms, what does that mean? Absolutely, if you're doing stats for a client, they are going to want that translation most of the time. So keep that in mind. I like to joke, but it's true. Stats is half interpretation, half translation. It really, really is. So that is going to be okay. So types of T procedures. So once you've determined, okay, I have quantitative variable. Quite honestly, we're looking at 1 for now. And we do not know the variability of population or populations. We only have sample info. Usually the big old giveaway that you're going to start using t-methods and not z-methods for means is that you only have the sample information. We may not even give you the explicit like, oh, this is the sample mean, and this is the sample standard deviation. But if we tell you you only have sample info, you have to go with t. So from there, you determine, okay, do I have one population, two populations? Future weeks, we'll worry about more than two. So if you have one, you're going to do like a one sample t-test. You can also do one sample t procedures for confidence interval. Obviously, you don't have to only test, you can do confidence intervals. Versus if you have two populations, then you have to decide, are these two populations independent from one another? So no observations in population 1 are also in population 2. Or are they dependent? Like, are they matched? Is every individual like in both samples? So if you determine they're independent, you're going to do a two sample t-test. So your parameter of interest will be mu1 minus mu2. If you determine they're dependent, so they're paired, you're going to do a match pairs methods on the differences. So it could be a match pairs t-test. It could also be match pairs confidence interval. Use a t-star critical value. So those are our t procedures for this week. We're going to go into robustness of t procedures next.